So the question says lithium atom has 3 electrons and they can be present in the following configurations: 1s squared 2p, 1s 2s 3s, 1s 2p 2p. So we've got 3 possible configurations, and I'm going to write them down here. One s squared 2p, 1s 2s 3s, 1s 2p 3p. Okay, there are 3 possible transitions you can take between these 3 configurations, which I'll draw. You can go from there to there, there to there, or there to there. I just want to consider, going to let each of you think for a couple of minutes of which each of these 3 are potentially allowed or forbidden between the whole configurations. You get lots of terms in each of the configurations. You may get different rules, but there's overall rule which tells you whether each of these transitions is allowed or forbidden. So let's just have a little think about that. Okay, so according to my, oh right, sorry, that's, I know what I have to do. I have to do this. There we are. According to my rather strange numbering system, this is lecture 3, and all that means it's block number 3 out of my courses. So we're now dealing with vibrational motion in molecules, which are normally called infrared spectra, because that's where they occur. Is the thing in? Yep. So vibrational spectra, which everyone always refers to as infrared spectra because they normally occur in the infrared. They're not absolutely always. So if I can remember you, you've already seen this slide a few times. Molecule has 3 n degrees of freedom, 3 translation, normally 3 rotations, sometimes 2, and the remaining ones are vibrational motion. So you get either 3n minus 6 or 3n minus 5 degrees of vibrational motion. And what that means, if you think about it, is the number of vibrations you get goes up rather rapidly with the size of the molecule. So if you have 2 atoms, it's 1. If you have 3 atoms, it's generally 3. If you have 4 atoms, it's 6. If you have 5 atoms, it's 9, and so on, going up. And from my point of view, calculating these things, basically every extra vibrational motion increases the complexity of the calculation by an order of magnitude. So diatomics are relatively simple, triatomics are fairly straightforward, tetratomics are okay, and when you get beyond that, it gets incredibly expensive. So we already looked at this picture. The other picture, this is water, in case you hadn't guessed. The other picture is vibrational modes. The advantage of doing triatomics is I can wave my arms around. And so when I'm doing water, and I've already done this is oxygen, these are hydrogen, and water has 3 vibrational modes, which are a symmetric stretch, a bending mode, and an asymmetric stretch. And actually, I've not been very accurate because I didn't move my head in any of those. And the reality is all those motions have to keep the center of mass in the same place. So I can't do this, for instance, without moving my head in the opposite direction, which I'm not very good at. There's Indian dancing, which is rather good at this, moving your head around as you move your arms around, but I was never trained in it. So those are the basics of vibrational motion. We'll just go through this, the various properties in order. So vibrational motions involve displacement from equilibrium. So you have an equilibrium geometry. Water has not a very high symmetry, but has a reasonably high symmetry equilibrium geometry in the sense it's C2V in point group symmetry, or if you prefer permutations, you can just swap the 2 hydrogen atoms and they're invariant. Of course, if you distort the molecule, you can break that symmetry. And you normally use things called normal modes to represent these motions. Now, I'm not going to go through the process of deriving normal modes because it's quite, in some ways it's simple. The results actually you can do most of the work analytically, but the actual derivation of them is slightly complicated. And I think it's fairly standard in a book, but you have these normal modes, degrees of motion. like other spectra, they're basically dipole driven. But here in the rotational spectra, it was a permanent dipole. So you just looked at the fixed geometry and said whether the dipole. In vibrational motions, it's a change in the dipole. So when you do the motion, does the dipole change? Another way of looking at it sorry. That's wrong. For mode number n, traditionally vibrational modes are denoted Q. For mode number n, does its derivative of the dipole 0 or not? So if there's a change in the derivative of the dipole as you move the molecule, then it's an allowed transition. If there's no change, you get no transition. So if we look at the first system we have here, hydrogen, we've already established it doesn't have a dipole at equilibrium. Does that change as you move the molecule? No, because you're preserving the symmetry. The two hydrogens are still identical. So hydrogen does not have a dipole. Every other one of these has some motion which has a dipole in it. Doesn't mean they have all the motion. So if you look at, no, water's a bad example because they all have dipoles. CO2. So just leave a triatomic because I can motion them. So CO2 is linear. Now this is carbon, 2 oxygens. This does not change, this motion does not change the dipole because it's still symmetric. So that motion is dipole forbidden, but you have an asymmetric motion like this, and that's dipole allowed. And similarly, when you bend the molecule, that creates a dipole. It goes from being 0 dipole in this direction to having a finite dipole. So if we ask the question, which of these have dipole moments? The answer is all of them except hydrogen, at least in one direction. So obviously if you have a heteronuclear diatomic, so 2 different atoms, it's quite obvious that that has a permanent moment and it will change as you move it. It may change by a very small amount, in which case you get a weak, but it'll never be identically 0. CO2 we've just been through. CH4 has a loss of symmetry. It has only 4 modes, even though it should be 9 because of degeneracies, and 2 of them are allowed and 2 of them aren't. And interestingly, just as my comment about Wikipedia yesterday, I was just trying to remind myself which 2 were allowed, and I asked Facebook, and Facebook now doesn't, sorry, not Facebook, Google. Google now doesn't want to give you a load of answers. It wants its AI tool to give you the answer to your question, and it gave me exactly the wrong answer. So it told us, I can't do this very well. Let's see if I do a methane. Sorry, it's a tetrahedron. The motion where everything goes in and out simultaneously doesn't have a dipole. It's a symmetric stretch. It preserves the symmetry just like the symmetric stretch in CO2. It told me that was infrared active, and it isn't. So be a bit careful when you ask these technical questions to the machines. Okay, so methane, H3 plus, equilateral triangle. That actually has 2 modes. It has a breathing mode where the whole molecule expands. That doesn't change the dipole. And then it has a bending mode, which is degenerate. So you can bend in 2 directions. And that's the only mode that's allowed in the system. Ammonia, everything's allowed. Phosphine is the same shape as ammonia. Water we've done. And formaldehyde, again, they're all allowed. There's not much symmetry there. So most of these have fairly strong infrared spectra. I don't know why I've done it again in highlights. So not necessarily all modes are infrared active, but some are in all those ones which are red. And actually there's a rule, there's something called Raman spectra, which is 2 electron. And if you have a center of symmetry, if your mode is not infrared active, it's Raman active and vice versa, but we won't go into that. So the normal modes of water, which I've already waved my arms around, look like that. And it's slightly small. Can you read that at the back, those numbers? So the symmetric stretch and asymmetric stretch are quite close to each other, 3676 wave numbers and 3667 wave numbers. So they're fairly near in energy. And actually, there are, if you isotopically substitute here, so you put a deuterium on, you get local modes where it does that and it does that effectively within the constraints that the center of mass has to stay in the same place. And then the bend is a little under half both of those energies. And we'll come back to those near degeneracies because it has significance. CO2, again, I've waved my arms around here. In this case, the asymmetric stretch is much higher energy than the symmetric stretch. And then the bending mode is relatively low energy, but if you look at it, two of those is almost exactly that. And that's called a Fermi resonance. And Fermi resonance is now a general phrase. It was Enrico Fermi observed that certain motions were in resonance like this. And actually, this is not just a quantum mechanical phenomenon. You get the same thing with planetary orbits, for instance, which you can have a planet which orbits, one orbits 4 times at the same time as another one orbits 3 times. So they actually have an interaction between them. So these interacting modes are generally called Fermi resonances, but this was the original one. This is the molecule Fermi originally analyzed as CO2. Right. So I've got a little bit more work for you to do. I started at the back yesterday, so let's start at the front today. Who wants to have a go at ozone? If you don't know what the structure is, just ask me. Should we start here? Any idea? Ozone got any infrared active modes? Yeah. So ozone looks like that. It's not an equilateral triangle. It's asymmetric. So has it got any infrared active modes? Yep. So it has 2 infractive modes actually, bending and the asymmetric stretch is infrared active. N2O, that's a linear molecule. Lady here, N2O, any ideas what that's got? Sorry? So in this molecule, every mode is infrared active. So the symmetric stretch is indeed, you don't normally call it like that. You normally say there's an NN stretch, an NO stretch, and a bend. Like that, but they're all infractive because they all change the dipole. So the original dipole is along here. Sorry? Yeah, so all of those different motions, if you've got this middle end, that's the end N. If you do the O like that, that changes it. If you do the N like that, that changes it. If you bend, that changes it. So they're all infrared active, okay? NO2, are we? Gentleman here. That's a bent molecule. Yeah, I think that's right. All of them. They're all infrared active. Bobby, do you want to do silane while you're sitting there? So, silane is the same as the methane. Do you remember what the answer was to methane?
Yeah. So you have a symmetric stretch.
Yep. You have an asymmetric stretch and you have an asymmetric bend. Basically, there are 2 types of bending modes. One preserves the symmetry, one doesn't. NO, where are we? Gentleman there. NO. Yeah, it's just, there's only one bend. It's only one stretching mode. It's infrared active. O2, no, very good. SO2, sorry, SO2, where are we? Only there in white. SO2 is like It's like ozone. Sulfur is just one below oxygen in the periodic table, so it's bent. I still can't hear you. A bit louder. So the asymmetric mode indeed is infrared active, and so is the bending mode. In fact, I think they're all infrared active because it has a dipole anyway. So when you do this, it just changes that dipole. Okay. Benzene. Right. Do you know what benzene looks like? It's got 12 atoms, so it's got rather lot of modes. In principle, 612s are 3n minus 6, so it's 36. It's got 30 modes. Now, quite a lot of them are degenerate. So indeed, it does have at least two different sorts of symmetric stretching mode. Do you think they're infrared active or not? No, indeed. So it's very high symmetry. So when it just expands and contracts, that doesn't change anything. But it has all sorts of bends and wags and torsional modes, which are infrared active. And it's too big. I'm not going to go into great detail. But you basically got formaldehyde. Where are we? Infrared active. I think all the notes are infrared active. Acetylene. That's an interesting one. This is a linear molecule. Any ideas on acetylene? What have we got there in terms of vibrational modes? Sorry, it's your turn. It's your turn. Yeah, of course. Acetylene, any ideas what we have in terms of anything which is allowed? So the symmetric stretch indeed is not infrared active. How about other modes? This is. You have a bend, right? So, for instance, if you bend the molecule, does that create a dipole? Yeah, it does. Because if you think of it, if you make a molecule look like this, you have a dipole in this direction. So it has an instantaneous dipole. And there are actually two bends. That's the one where they go the same way. And then they'll have one which go the opposite ways as well. But that also makes a dipole. Actually, I'm not sure it does. Maybe it doesn't. I'd have to think about it. I think maybe it doesn't. Phosphine. Phosphine is sort of like ammonia, except the ammonia has a tunneling inversion and phosphine doesn't. So phosphine is a pyramid. Where are we? Lady in the green. Sorry? So do we have any infrared active modes in phosphine? Yeah, okay. In fact, I think they're all infrared active. There are 4 modes, and I think they're all infrared active. CS2. CS2 is linear. It's like CO2, actually. So the symmetric stretch is not active, and the other ones are. So the asymmetric stretch is better. So take-home message. We only had one molecule here which didn't have a dipole allowed vibrational spectrum. If you have more than 2 atoms, there's always some way you can distort the molecule to make a dipole, no matter how symmetric you started off. So even something like C60, which is incredibly high symmetry, you can still distort it to get an infrared mode. Okay, good. Right. Anyone here play the piano? Nope. We had a very fine, no, the lady's not here, we had a fine rendition of your national anthem yesterday. Oh, that was you, yeah, sorry. But I think Indian harmonics are different from European harmonics. So probably the language used for harmonics is also different. So these are harmonic motions. And actually the language used to describe them is the same as the language used certainly in European harmonics. So things like overtones is actually I don't know, is this used in Indian music at all? Maybe not. In European music, it's a standard expression. And, and a piano string is actually fixed at both ends. and it has finite waves going across them. And an overtone is simply when you have double the number of waves going down the same length of string. And this is the same here. It's a so the fundamental bands, and obviously you may have several of them in a molecule, involves changing a quantum by 1. Okay, and if it is allowed, and we've already established in everything except symmetric diatomics, you always have some fundamentals allowed. If it's allowed, that is generally the strongest band. Okay, and that's the one which the first derivative has to be not 0 for. Okay. You can then put more than one quantum, for instance, 2 quanta, in one of these modes, and that's called an overtone. They tend to be about an order of magnitude weaker for every quantum. So you go down maybe a factor of 8, factor of 10, factor of 12 between the fundamental and the first overtone. I'll show you a picture of ammonia in a couple of minutes, and you'll see it in the picture. It's seeing is better than me speaking about it. You see it very quickly. You get combination bands, and that's also used, I say, in harmonics, where you actually combine 2 harmonics. In other words, you excite 2 modes at the same time. They're also weak. They tend to be weaker than overtones, but they still occur. And then you get hot bands. And hot bands are ones that don't start from the ground state. And, yep. So, yeah.
That's a very good question. If I go back a minute, there are lots of different notations for doing this. I'm sorry, I'd be flipping between
notations. So, V1, V2, V3, sometimes written so sometimes you write the states like that. So the ground state is 0, 0, 0. That means you've got no quanta of excitation in any mode. If you want to excite the asymmetric stretch, that would then be written 0, 0, 1. That would be 1 excitation, and that would be 1, 0, 0. 1 excitation, and that would be 1, 0, 0. Okay? There are at least 2 other notations, I'm afraid. I will try and restrict myself to these 2. But there are different ways of writing exactly the same thing. So yeah, good question. So I've just written it this way for it's an easy way of doing it. And I've done everything in terms of the leading modes, but it applies to any mode. So when I say the fundamental is 1 here, it's 1 in any of these columns and 0 anywhere. That's just the new 1 fundamental. You get a new 2, 3. So you get, if you've got 6 modes in a molecule, you get 6 fundamental bands in principle if they're all allowed. And you get obviously increasing numbers of overtones and combination bands. Right. The general assumption is that at atmospheric temperature, everything is in its ground state. And that's true, I think, for pretty much all the molecules we considered. Possibly not the funny modes in benzene. Because you can get some modes which are very low temperature. But normally they take 1,000 degrees or several hundred degrees to warm them up. So the convention is that if you start from something that is already excited, that's called a hot band, because it's assumed it happens at high temperature. For heavy, the band scale with mass, we'll talk about that in a minute. For heavy molecules, that may not be true. And also for the strange organic molecules, we get rotors and things which can be very low energy. It's also not true, but that's the language. So the general, yeah.
In the combination, yeah. So it just means that you get excitation in 2 different modes. That's all I'm trying to represent there. So a combination band is one which has, if you start from the ground state, has excitation in 2 different. So if you're doing water,
you may be exciting both the bend and the asymmetric stretch at the same time. So maybe doing that, and sorry, I'm not good enough to wave my arms around like this, but you may excite both those modes at the same time. So that's why I put numbers in 2 columns. So combination band involves excitation of more than more than one vibrational mode at a particular time. Okay? Does that make sense? Vibrational motion is not entirely harmonic, but it's the absolute starting point that it bases on a harmonic oscillator. And I realize I didn't put lots of pictures of harmonic oscillator wave functions in here. I'm going to have to draw them here because we will need them for later lecture. The harmonic approximation, so if for a diatomic, a harmonic potential looks like that. And the vibrational levels are evenly spaced. And you count from 0. The ground state has 0 excitation in it. So this is just a ladder. The reality is slightly different, that they get slightly closer together as you go up. I've drawn that too much, but they're slightly what's called anharmonic. They get a little bit closer together, but it's by a small amount. Okay, so if you do excitation from 0 to 1 is not exactly the same as excitation 1 to 2. The 1 to 2 is a slightly smaller gap. So the general harmonic formula is the one I've written here. The energy is given by what's called the fundamental frequency times n, where n is this number I've put up here, plus a half. And I've snuck that half into you, but it's actually rather important. What this means is you cannot have 0 vibrational energy. So even when you're in the ground state, you have this thing which is called the 0 point energy. And that has consequences which it leads to something called fractionation. And I think I'll take a time out and go through that now. So as I can make out, the only way writing on this board is to get a blank slide. So I will make a blank slide. Oh, I need to. So we've discussed there's an awful lot of hydrogen in the universe. There's a little bit of deuterium, about 1 part, maybe 3 parts, 2 parts in 10 to the minus 5 relative to the hydrogen. But you can imagine a chemical reaction which looks like this. H2 plus deuterium is somehow in equilibrium, with that. Okay. Now, if you're at high temperature, this is going to be, well, if there's only 1 part in 10 to the 5 of that, you're going to be almost entirely in this with a little bit of deuterium. At low temperature, that's not true because the 0 point energy of this is significantly bigger than the 0 point energy of this. So the vibration, again, give very approximate numbers here. The vibrational fundamental of this is about 4,400 centimeters minus 1. I didn't do my homework and work out what it was here, but let's say it's 3,800. That may or may not be correct. Then basically, that's a whole quantum, so you take a half a quantum, the 0 point energy would be 2200. 0 point energy here would be 1900. That's the right order of magnitude. It is about, this reaction is about 300 wave numbers exothermic. So actually, you gain 300 wave numbers by going on that reaction. The interstellar medium is incredibly cold. It's at 20 Kelvin, going down even to 5 Kelvin in some cases. At that temperature, this is a lot of energy. So at low temperatures, you very much favor deuterium in your molecules. So to give you an example, you can do the same thing with ammonia. In fact, if you have NH3 plus HD, you'll go to preferably NH2D plus H2. That is also energetically favored. And despite the fact that deuterium is 1 part in 10 to the 5 hydrogen, ND3 is an observed interstellar molecule. If you think about it, if this was just statistical, for every NH3 you get 10 to the minus 15 of these. It'd be completely impossible to observe it, but actually it's observed less than NH3, but not hugely less than NH3. And you can get, there are theoretical predictions, though I don't believe it's been confirmed by observation because D3 plus is very difficult to see. There are theoretical predictions which say that the very coldest cores, D3 plus should be more common than H3 plus, which is kind of amazing because that would be again 10 to the minus 15. This is H3 plus is very hard to see, so no one has seen the D3 plus. But there are when people do models, the interstellar medium. So this process is called fractionation. You actually get it in planetary atmospheres. So for instance, we have meteorites that come to Earth from various places. And we know that some of them come from Mars. I don't know the mechanism whereby Mars is chucking bits of rock out of itself, but we know that some of them come from Mars. And a characteristic of Martian meteorites, sorry, let's draw that again. Is that 15N to 14N is much bigger in Martian meteorites than it is in Earth meteorites. And this is caused by fractionation of nitrogen in the atmosphere. In particular, Mars doesn't have as big a gravity as Earth, so it loses gases more easily. By the same logic, D to H is also much bigger on Mars than it is on Earth. I think deuterium is approaching 1% on Mars compared to Earth, where it's 10 to the minus 5. And it's caused by the fact that the gases will differentially escape. If they're lighter, it's easier to get the escape velocity. And you do that over billions of years, and you end up changing the isotopic composition. So fractionation is really important in the interstellar medium, but it's actually found in our own atmosphere, in other planetary atmospheres around here. And it's an artifact of something very simple called the zero-point energy. And the zero-point energy is a consequence of Heisenberg's uncertainty principle. So we're celebrating 100 years since Heisenberg invented matrix mechanics. And one of the consequences is that if you have a harmonic potential like that, and if you're able to sit just here, you would know you'd be in this position, that the uncertainty in the position and the uncertainty in the momentum would both be zero. Because if you sat at the bottom of that patel, you wouldn't be moving, so you'd have no momentum, and you'd know exactly where you are. And we know that the uncertainty principle says that delta x, delta p must be bigger than h cross upon 2. And that gives you directly the zero-point energy. Yep.
The mass sharing. Yeah, I realise I hadn't done it. We're coming to that. Yeah. It's a very good question. And it depends on the square root of the mass. I'll show you in a minute. I probably should have done that before I launched the fractionation. It depends on the square root of the mass. The square root of the reduced mass, to be more precise. Yeah, so actually this...
Atoms have zero-point energy, you just never talk about it like that. So if you think of the hydrogen atom, you have a nucleus here, and you go, nucleus here, so R equals 0, and you think of the Coulomb potential, it's minus infinity here, and it looks like this. and we're talking energy level somewhere here, and you have a very big, if you like, 0-point energy. It's just never described in those terms. But you don't have an electron trapped right down at the bottom here of the energy world. So similarly, there's energy stored in there. And the joking comment I made yesterday about n equals a half quantum numbers would actually, the idea was you could release this energy by getting your atoms stored here instead. You can't, because n equals a half quantum numbers don't exist. But there was a whole model based on the idea they would be. Anyway, that's a side thing into fractionation. Let's get back to the talk and define, amongst other things, the mass. So that was fractionation. That's just a spectrum of ammonia, and forgive me, it's plotted double. It's actually taken from one of my papers, and I think the red is experimentally observed and the green is what we were calculating. So it's not that spectra appear as mirror images on themselves, it's just us showing our results against experiment. So you have the rotational spectrum here, and I've lost the wave number off the bottom, but I do have wavelengths up here. So this is 1,000 wave numbers. Oh, sorry, they're in the middle here. So this is a rotational spectrum at very long wavelengths. Two fundamentals you can see here, very strong. Overtones, you may not even be able to see that at all from the back. This is a linear scale. People normally plot them on log scale so you can still see them, but it just gives you an idea how these things go down in intensity as you, so basically this is where the action is, but actually this shouldn't be ignored. And I'll show you with water in a minute. Water is particularly anharmonic, where the overtones go to. But before we do that, I want to talk briefly about polyads. So I already mentioned that you quite often have the example, for instance in water, that two bends is nearly the same frequency as both the symmetric stretch and the asymmetric stretch. That means that instead of the bands being nicely separated, they lie on top of each other. And quite often, normally for fundamentals you can sort them out, but quite often as you go up in energy, they get increasingly entangled. And people talk about polyads, where they say that actually the amount of vibrational energy you've got in, for instance here, if you have polyad n, it's the number of quantum in the symmetric stretch, half the number of quantum in the bend, and the number of quantum in the asymmetric stretch. Now, one of the problems with the polyad notation is it seems to be unique for every single molecule. The water one has this rather thing of using half integers. Most other ones would say two of those, one of those, and two of those, and then keep it all integer. Water, for some reason, doesn't. So that polyad 1 can have one quantum in that, or two quantum in that, for instance. It can't have any mixtures. But if you go to polyad 1.5, then you add a bending mode, you get this. I don't have polyad 2, but if you have polyad 2, you could have two quanta there, one in each of them, and then a whole variety of ones with bends in. So they go up very rapidly. And if you ever had the misfortune to discover methane, to work on methane, the naming convention of the polyads is appalling. They're named after the degeneracy of the polyad in Greek. So what your Greek is for 120-fold degenerate polyad takes a bit of challenging. I had a PhD student working on methane who's just finished. She had a big advantage over the rest of us. She was Greek, so she actually understood all these things, but it's a really strange convention. So unfortunately, as I say, this polyad convention seems to be molecule specific. So if you work on one molecule, you just have to learn how people describe the polyads. But I won't go beyond water here. So as I say here, water, methane, ammonia all have pronounced polyad structures in them, and you can label the things by polyads. Consequence of that in the Earth's atmosphere, you've already seen this picture, and that's vaguely said that you get these interruptions in the infrared. They're virtually all to do with water. And they actually are the polyad structure of water. So the clumps are not single vibrational modes, they're lumps of vibrational modes put together. So starting at long wavelength, 10 microns, that's just the bending mode. With this funny notation, if you have an odd number of bending modes, it's called delta. That's the stretching modes with also 2 bends, stretching fundamentals 2 bends. That's combination band, say 1 stretch and 1 bend, or 3 bends. That's an overtone band, 2 stretches, 4 bends, and that's a mess. But they go up all the way through. In fact, you can see them going even into the ultraviolet. You go up right across the, right across the observed spectrum. And to be honest, if that wasn't true, I probably wouldn't even mention polyads at all. So vibrational motion largely sits in the infrared. In water, rather unusually, it's quite important in the visible, but that's not normal. There are no rigorous selection rules on the vibrations, but there's a strong propensity that changes by 1 are strongest. It's normally order of magnitude stronger, but it doesn't mean the other ones are forbidden. They're not like difference between allowed and forbidden transitions, which should tend to the 10 or 8 orders of magnitude. There may be 1 order of magnitude difference. So the fundamental is always 1 change in the quantum, normally implicitly from the ground state to excited state. They have very characteristic regions they sit in, and actually, if you look at organic molecules, things with carbon backbones, they have a lot of vibrational modes that all sit in the same place. And so, for instance, oil companies are rather interested to know what they get out of the ground in terms of their oil, and they use spectroscopy for this. But actually, once you get beyond 5 carbon atoms, all the spectra look the same. So we get 6, 7, 8 carbon atoms in the molecule. Actually, they can't separate them because they all basically have C8 stretches in the same place, CC stretches in the same place. And essentially, they don't get a fingerprint from C6 against C8 from this. So for instance, hydrogen stretches tend to lie in this region, 2000 to 3000 wave numbers. That's a region that James Webb is busy observing at the moment. So we're beginning to get information on that in space from molecules. I said that you rely on the derivative of the dipole, and that's true, but actually the intensities always depend on dipole squareds. So it's actually the derivative of the dipole squared that matters to give you the intensity. It has to be non-zero to get an intensity at all. And they're always accompanied by rotational changes. And here, how am I doing for time, timekeeper? 5 minutes, okay. I think rotational changes after chai. Anyone got any other questions for me? I've already had a couple in this thing, but anyone else got anything else you want to ask? Yep. So
what's the value of that on harmonic? Right. So that's a good question.
I can answer it quite a few different ways. If we go back to yesterday's lecture where I showed the Hertzberg book. Just thinking a minute. Somewhere in here, I think, we had Hertzberg, didn't we? Yep, there it is. Right, so this is CO, okay? ground state, rotational constant, rotational constant 1.93 wave numbers, fundamental frequency 2169 wave numbers. We still haven't got onto the mass effect here, but that's lower than the hydrogen simply because it's carbon and oxygen, so they're heavier. And harmonic term here, 13 wave numbers. So basically, you're changing as you go up by approximately 13 wave numbers out of 2,170. The effect on the harmonic 0-point energy will be half that. So the anharmonic effect will be about 6.5 wave numbers out of 1,300 or something. No, sorry, 1,050. It'd be about 6.5 wave numbers. So it's there. It's not huge, but it's slightly an anharmonic effect. Now, was that the question you asked me? Yeah. So there's a 80 wave numbers. So it's less than 1%. I think that's less than 1%. Yeah, it's about 0.5%, something like that is the effect. I have to say, I don't do it like this. I have got a little thing at the end of this lecture on actually how I don't use the harmonic approximation. We solve the Schrödinger equation directly, and then you don't have to worry about. And this is what he lists here is the first order harmonic correction. There are higher order ones, but they get small. In well-behaved molecules, and CO is a very rigid molecule, so CO is a very well-behaved molecule. It has a very large number of vibrational states. They're known experimentally up to 40-something, but they go higher. Then actually doing an expansion, a harmonic expansion is quite accurate, but actually for other molecules it's terrible. H3+, which I spent quite a lot of my life, and I'll talk about that briefly, actually it's very anharmonic. It's a horrible way of doing it. So we just solve Schrödinger's equation directly. But there is a small anharmonic effect on the 0-point energy, which is what you asked me. Anyone else got anything before we have a chai break? Okay, see you in 15 minutes.